Great. Thanks very much. It's been a lot of fun being here, and I've learned a lot from the various talks and talking with all the participants of this conference. So I want to tell you about two papers. One is a paper that appeared last year with Sven, and another is work in progress with Anirudh and Terry Gannon. And I was inspired by Nadi committing to a third digit in his archive number, so I decided to do the same. But then I got anxious and I decided to take away this the second digit, to give myself a little 5-year cushion. And I also want to thank various people who are in the audience, with whom I've had many discussions and some ongoing projects, and they've influenced my perspective a lot. So earlier in this program, Ichul gave a beautiful overview talk, and one of the questions that he posed at the end to high energy theorists was the question of how can we find all the symmetries? So if I hand you a quantum field theory, most people in this audience have their favorite ways of obtaining examples of topological defects in that quantum field theory. But generally, we can't really say whether the sort of examples that we produce are kind of exhaustive, whether we've found them all. If you add the word invertible, then oftentimes we think we know what the full sort of symmetry group of a theory is, but if you relax invertibility and you allow yourself to consider non-invertible defects, then we generally don't know. And an a priori sort of independent question, which is a very old question, is how can we find all of the conformal field theories? How can we classify all CFTs? Perhaps you might want to make your life easier by restricting your attention to a given central charge, and then you're interested in sort of carving out the conformal manifold at that central charge. And one of the themes that I hope to emphasize in my talk is that these two questions are not independent. They're very much attached at the hip. So that's sort of the big motivating questions. And so I'm going to be in 1+1 dimensions in this talk. And I'll say a little bit about full conformal field theory with both left movers and right movers. But a lot of the results that I'll state will be at the level of chiral algebras. So let me remind you what a chiral algebra is. So a chiral algebra is this sort of structure that you can associate to a 2D conformal field theory, which just consists of the holomorphic local operators of the theory. And every 2D CFT has a non-empty chiral algebra simply because the stress tensor is always in it, and also the derivatives of the stress tensor and all of its descendants. So you always have sort of this big infinite dimensional algebra lying around that you can organize the physics with respect to, and that's what we'll do. Amongst all chiral algebras, there's a sort of particularly nice class of so-called rational chiral algebras. And these are essentially chiral algebras whose representation theory is very nice. So they have finitely many irreducible representations. And furthermore, their representation theory is semi-simple. So any representation can always be decomposed into a direct sum of finitely many simples. And the way that I'll think about chiral algebras in this talk is a sort of picture that goes all the way back to Witten, and many people in the audience have sort of developed this picture farther over the years. And so the way that I want to think about a chiral algebra is that it furnishes a kind of gapless chiral boundary condition of a bulk 3D TQFT. And that 3D TQFT is defined by some modular tensor category, and that modular tensor category is simply the category of representations of this chiral algebra. And physically, the reason the sort of bulk TQFT is to be identified with the representation category is that given a bulk topological line operator, you can associate a representation of the chiral algebra, which is simply the Hilbert space of local operators on the boundary on which this anion can end. Okay, so this is an overview of chiral algebras. Are there any questions?
I thought in general you can have a V which is a representation category is not identical to this BV. That's possible.
in the way that I think about it, it's not, but I know we have some different perspectives on this. Yeah, I think, how to say? Yeah, maybe we can discuss offline. Yeah, that's going to sort of be my assumption here, is that maybe if in your language, I'll always be restricting to this particular class of chiral boundary conditions where you can make this association. Yeah.
In general case, these two categories can be only weight equivalent.
So maybe it'll become clearer. So I'll actually later on I'll do something that looks like what you're doing, but I'll sort of interpret it a little bit differently. So ask me again in a few slides. Okay, so why talk about chiral algebras instead of full CFTs? So first, actually, let me say what the kind of main result is going to be. So I'm going to restrict to chiral algebras whose central charge is equal to 1. And under some assumptions, I'm going to sort of tell you all the finite rank fusion categories of line operators that are supported on the chiral algebra. So essentially, I'm going to classify all finite rank categories of topological line operators in C equals 1 RCFT. The assumptions are, or caveats are that one, I'm not going to try and probe the F symbols in all cases. I'm sort of going to do the classification at the level of fusion rules only. And to be completely honest, we're still working out a few of the exceptional cases, but we're pretty close to being done. And the most important assumption is that I'm going to make an assumption about the classification of C equals 1 rational conformal field theory. That's sort of all the theories that we've discovered so far are all the ones that exist. And I'll say more about this assumption in a bit. Okay, so why this and not a result about full CFT? Unitary, yeah. I should add the word unitary. Thank you. So one fact is that chiral algebras are sort of building blocks for full CFTs. So if you understand something about topological line operators of chiral algebras, then you also understand something about topological line operators of full conformal field theories. And the second thing is that if you're a condensed matter physicist, then maybe even the chiral algebra is kind of interesting in its own right. So oftentimes you don't have a full conformal field theory, but rather you have some bulk 2 plus 1D topological phase, and it has some boundary, and there's some edge modes, and people are interested in this setup for various physical reasons. A high energy theorist would understand chiral algebras as sort of the simplest example of a relative quantum field theory. That is a quantum field theory that's attached to a bulk in one higher dimension. And understanding symmetries of relative quantum field theories is, well, there's more moving parts to it, and I think there's some intrinsically interesting things there as well, about which I'll say more later. And if you're a mathematician, of course, VOAs and chiral algebras give you a lot of beautiful mathematics, a lot of category theory, and maybe one small tidbit today is, if I get to it, is I'll give you a kind of cute analogy with Galois theory, like the Galois theory that you study in as an undergrad. Okay, so I obligatorily must flash this picture again. I won't even write the words. Let me gesture at the two motivating questions. How do we find all the symmetries, and how do we classify all the theories in a setting where we sort of have pretty good control over them? So that setting is the setting of C less than 1 conformal field theories, which are known as the minimal models. So it's a beautiful result of theoretical physics that we've completely classified all the C less than 1 conformal field theories. And maybe part of the reason that we were successful is because each central charge supports only finitely many theories, so it's a little bit more tractable. And similarly, we sort of know for each theory what all the topological lines are. So for example, for the Ising CFT, we know that every topological line belongs to this Z2 Tambari-Yamagami category. And these two statements are sort of, they're not completely unrelated. So the relationship between them goes through the following fact. So this is a general fact. If you have a single example of a CFT that's built on some rational chiral algebra V, then it turns out that you can reach all the other CFTs that are built on top of that same chiral algebra by gauging. And the thing that you gauge is this category of Verlinde lines, which by definition is the sort of category of topological line operators of the theory that commutes with the Chiral algebra. So in a sense, you only need to know one theory and something about its symmetries, and then you kind of have all the other theories for free. And in the context of these minimal models, the way that this works is the Virasoro itself, the Virasoro algebra itself is a rational VOA, and a CFT built on top of the Virasoro algebra is just any CFT. So you can simply start with the diagonal minimal model, figure out all the ways of gauging it, and then you reach all the other theories. Okay? So when C is greater than 1, it's sort of the opposite situation. We know almost nothing. So for example, there's I claim there's no unitary compact CFT with central charge greater than 1, for which we know the full category of topological line operators. And similarly, there's no value of the central charge where we've been able to completely carve out the conformal manifold of theories. In fact, sort of the stupidest questions you might ask we don't know the answer to, like, is there a continuum of CFTs above C equals 1? Is there a gap? Is there a limit point? Extremely coarse questions we still somehow don't have access to. Yeah. Is there a question?
Making some extra assumptions, like Liouville theory is a continuum of C.
Yeah, I'm assuming unitary compact.
Oh.
Yeah. So, yeah, I don't want to consider things like Louisville here. Yeah, thanks for the question. Discrete spectrum. So rational theories are compact. There's some irrational theories that are known that are compact, often free or supersymmetric.
Sorry, but if you have some extended symmetry like a or multiple, so they are known, right? I mean,
those are examples of CFTs, but they certainly don't exhaust all of the CFTs. So maybe you're saying once you fix a West-Zumino chiral algebra,
yes,
you know all them. Yeah. So, but I'm taking theories whose chiral algebra is just Virasoro, and I'm not making any assumptions about an extended symmetry algebra.
Okay.
But even there, we might not know all the topological lines, just those that commute with chiral algebra.
That's right. So it's a common misconception. So Clay pointed out that in our CFT we don't know all the topological lines, and that's true. It's a common misconception that the category of Verlinde lines of the RCFT is all the topological line operators. But there's a simple counterexample. Take SU2 level 1. It clearly has SO4, it has continuous symmetry, but the Verlinde lines only see a Z2 subgroup. So yeah, in general, there's more to life than just the Verlinde lines of an RCFT. Thanks for the comment.
You only refer to TDL to preserve the most.
Yes, I just want topological lines that preserve Virasoro. So the difficulty in answering these two questions, you might think, is the same difficulty. So here's an expectation. If I this is fluff, so take it with a grain of salt. But if you kind of generalize this this thing I told you on the previous slide about moving around theory space by gauging, then what you might expect is that if you start with any one theory and you somehow manage to determine all of its topological line operators, then you can reach any other theory at the same central charge by gauging that category. Let's call this the effective gauging hypothesis. Okay, so in practice, this doesn't help you that much because one fact is that you sort of have this expectation, maybe at least for rational, I might also believe it for irrational theories, that every theory with C greater than 1 has infinitely many topological lines. So that's comment number 1. So it's an unwieldy category. You might think that you could get away with just doing finite gauging within this big infinite category and get around theory space that way. But the problem there is that it's provably the case that finite gauging is not enough. So in particular, there are known obstructions to two rational conformal field theories being related by finite gauging. Namely, their left-moving chiral algebras should belong to the same width class. and I've drawn a picture of what it means for two chiral algebras to be Wood equivalent. It essentially means that their bulks should be separated by a topological interface. And it's just known that not all pairs of chiral algebras are Wood equivalent. For example, there's no finite gauging you can perform on the SU2 level 1 WZW model, which takes it to the bosonization of the free Dirac fermion, even though these two theories are rational conformal field theories. Okay. So it's generally hard, but C equals, sorry. Oops, oh my gosh. This point about the finite gauging not being enough?
When you say Dirac fermion, you mean the one with the sum of the superstructure?
Yeah, the bosonization. So I'm thinking about U1 level 4. So the R squared equals, so in the units where R equals square root of 2 is SU2 level 1, this is R equals 2, the bosonization of the Dirac fermion.
And what's the statement that you cannot go from square root of 2 to?
Yeah, you can't go, in general, you can't go from R to R prime with finite gauging unless the ratio of R and R prime is a rational number. This is a kind of CFT uplift of this fact. You know that U1 level N times U1 level M, Chern-Simons theory, doesn't always have a gapped boundary condition. So C equals 1 is a bit of an edge case. There's a kind of decades-old conjecture that at C equals 1 we maybe know all of the theories. So there's this belief that this picture sort of contains all of them. There's 2 branches and then 3 exceptional theories. And if you try and do the easier thing of just classifying the rational conformal field theories, then if you combine various results in the literature or use various ideas that appear in the literature, it appears like a proof is almost there, and but there's various gaps, and so we're trying to close these gaps, and that's work in progress. We think we have a strategy. I'm not sure if it'll work yet. And similarly for as far as topological line operators go, we have tons of examples. Ifan and Ryan did a very thorough investigation, and there was even a paper that appeared last night. One sort of cute thing that you can show is that if you make this assumption that the rational conformal field theories that we know are all of them, then every finite symmetry of SU2 level 1 is invertible. And that might lead you to speculate that, in fact, maybe every symmetry of SU2 level 1 is invertible, because we haven't seen any non-invertible symmetries yet. And if that were the case, by combining with this effective gauging hypothesis, then you might think that you could reduce the classification of C equals 1 conformal field theory down to this sort of kinematic problem of figuring out all the ways of gauging SO4. So we've been talking a bit about this with Hotat and Mitchell. And actually, if you go back and look at Hotat's talk, he sort of has already taken steps in this direction by showing that you can move along the entire circle branch via gauging. So the upshot is that the classification of conformal field theory and the classification of line operators in a given theory are 2 very closely related problems, and you might think that sort of carrying figuring out everything at C equals 1 is something you might hope to be able to do soon. So in this talk, I'm going to sort of go in one direction. I'm going to assume we've discovered all the rational conformal field theories at C equals 1. Again, hopefully there will be an independent proof of this soon. But under this assumption, I'm going to sort of algorithmically show you how to determine all the finite symmetries of C equals 1 theories. And of course, I'd love to be able to access the entire sort of full infinite continuous category of topological lines. But this is the best we can do for now, and perhaps you can think about this result as kind of approximating the full category of topological line operators in the same way that you can sort of approximate U1 by its Zn subgroups. So the basic tool that I'm going to use is this notion of symmetry subalgebra duality. which has appeared in various guises in the literature. This is maybe not the best name, but it's what I've been calling it. So to state what symmetry subalgebra duality is, let me first just note that the category of topological line operators supported on a gapless chiral boundary always sort of contains the bulk category as a subcategory, simply because you can push the lines in the bulk onto the boundary. And the situation here is slightly different from the case of gapped boundaries, because in the case of gapped boundaries, when you push, sometimes the line can split into two or more. But for these chiral algebra boundaries, it turns out they never do split. So it's a genuine kind of subcategory. And so my claim is that there's a one-to-one correspondence between conformal subalgebras of the operator algebra of your chiral algebra, W, and finite rank fusion categories that act. And you can be very explicit about the bijection between these two things. So if you have some symmetry category of line operators, then you're always entitled to produce a subalgebra by restricting to the invariant states. You can restrict to the local operators that commute with the lines in this category. And in the other direction, if you have a subalgebra, then you can obtain a symmetry by just considering all of the symmetries of the theory that commute with that subalgebra. So this is kind of chiral version of the Verlinde line construction. Okay, so this is kind of the main way that one can translate results about classification into results about symmetry. If you know something about classification, then you know something about all possible subalgebras, and you can convert that to something about symmetries. So let me give you some more details on how to reconstruct a symmetry from a conformal subalgebra. The basic idea is going to be that a conformal subalgebra allows you to draw this kind of sim-TFT picture. And so what do we have here? So on the left, we have this conformal subalgebra. It appears on the boundary of its own bulk. And I sort of recover this original chiral algebra V by smushing this topological interface onto it. And this topological interface exposes certain symmetry lines, so it supports certain symmetry lines on its world volume, and that's what I'm calling this Verlinde category. Okay, so in slightly more detail, good. So as I said, W is a rational chiral algebra itself, so it appears on the boundary of some bulk TQFT. V is a representation over itself simply because it acts on itself via the OBE. And therefore, since W is a subalgebra, by restriction, it's also a representation over W, a generally reducible one. But as we described earlier, representations of W are sort of the same things as anyons in the bulk. So from this, it follows that V defines a kind of distinguished anyon in the bulk TQFT that supports W on its boundary. And it's not just any anyon, but actually this anyon defines a condensable algebra object. Or I should say, it defines a way to gauge generally non-invertible one-form symmetries inside of this bulk TQFT V of W. And if you carry out this one-form gauging in half of spacetime, then you obtain some topological interface. And it turns out that if you fuse this interface onto W, then you get back V. Okay, so mathematically, this category of line operators is simply the A modules inside of this MTC V of W. And this distills precisely the line operators of this chiral algebra V that commute with this subalgebra W. And you can do a lot with this description. For example, you can instantly read off all the twisted sector Hilbert spaces and the way they act on local operators and so on and so forth. Okay, one cute fact is that this symmetry subalgebra duality gives you a very tight analog of Galois theory. So let me just take you back to undergrad algebra. So what did you do in Galois theory? So generally there, what one studies is this problem of field extensions. You have some base field and you have some bigger field that contains it, and you want to find all the fields that sit in between the two fields. And these are essentially controlled by group theory. So you can define this Galois group that consists of the symmetries of this bigger field that preserve the smaller one. And then you have that the intermediate fields that sit in between F and E are in one-to-one correspondence with subgroups of this Galois group. And the exact same thing is true for chiral algebras. The dictionary between sort of Galois theory of field theory and Galois theory of chiral algebras is that a field extension should be promoted to a conformal embedding. The Galois group is replaced by this category of Berlinde lines that I defined. And intermediate chiral algebras in between W and V turn out to be in one-to-one correspondence with sort of subcategories of this Berlinde line category, at least the subcategories that contain the lines in the bulk. Okay. Yes.
Asking about the analogy. So in Galois theory, we also discuss solvable groups. Is there an analog of this structure here?
Solvable groups. So you,
well, we can talk about it afterwards.
Sure. You've already exhausted. You've already exhausted my knowledge of Galois theory. Yeah. So let's apply this in an example. So let's say we want to, chiral boson, single chiral boson. Surely we should know all the symmetries of that thing, so let's try and reproduce them using this formalism. So when you talk about a chiral boson, you have to specify which vertex operators you include in the theory. And those generally belong to some charged lattice, square root of 2mz. And this m here tells you the level of the bulk Chern-Simons theory that supports the chiral algebra on its boundary. Now, except for some small values of m, if you believe this assumption about the classification of C equals 1 rational conformal field theory, then all the sort of conformal subalgebras take this form. So in other words, either a conformal subalgebra is another chiral boson theory whose charged lattice is inside of the bigger charged lattice, or it's one of these guys where this one is the sort of the states in the chiral boson theory that are neutral under charge conjugation. Okay, and so for example, if you just calculate what this Berlinde line category is that's induced by this conformal embedding, that's sort of all I need to tell you, because the symmetries that are induced by this subalgebra are contained inside the symmetries induced by this subalgebra. If you calculate this category, it looks like a kind of Tambari-Yamagami thing. So there's this this familiar factor of a cyclic group with m units of 't Hooft anomaly. And then you have some collection of duality lines that are permuted amongst themselves by the action of the invertible symmetries, and they sort of multiply together in this way. Okay, but for small values of m, there are some exceptional conformal subalgebras, and these lead to some exceptional finite symmetries. For example, let's consider U1 level 18, which supports a particular chiral boson theory on its boundary. Let me construct a kind of funny subalgebra for you. You can take SU2 level 1. This thing has an SO3 automorphism group. One of the exceptional finite subgroups of SO3 is A4. And you can look at the subalgebra of SU2 level 1 that is invariant under this A4. That's what I call VT. And it turns out that VT embeds into this chiral boson theory at level 18. And if you calculate what the topological line operators that are induced by this conformal embedding, then you find this thing that I've never seen before. If anybody can identify this category, I'd be delighted if it has a name. Okay, and then you can basically continue this algorithmic procedure for sort of all conformal embeddings, and that's what we're in the process of doing now. So for future directions, I think it would be interesting to try to finish the classification finally after 4 decades or so of the C=1 unitary compact conformal field theories and their topological line operators. Perhaps you might need to assume something like this effective gauging hypothesis, or perhaps you can kind of prove this independently. It would be nice to develop a complete theory of generalized global symmetries in the context of relative quantum field theories. Topological line operators won't be enough to sort of fully exhaust what this theory will give you. For example, one thing that I didn't discuss in this talk is that topological surface operators in the bulk can also act on local operators supported on the boundary. And this is, they should generate an algebra that's very much analogous to the tube algebra that I think is called the dome algebra in the literature, and we're discussing these issues with various participants here. And as I tried to stress earlier, you won't be able to get away with just gauging finite symmetries, so eventually we're going to have to confront the full glory of continuous and potentially even non-invertible symmetries. So, thank you.
Do you believe the effective gauging hypothesis is valid at C greater than 1?
Do I believe the effective gauging hypothesis?
Yeah.
Sort of, in the sense that, like, I think you could probably just rephrase what it means to have a CFT as a way to gauge the full category of Verlinde lines of the Virasoro algebra, whatever that means. But it'll almost be by definition. So the question is whether this perspective is useful or not. And I don't know yet. I don't have an opinion yet.
I'm not sure it's by definition, right? Because you have to discover the full category of lines of a given CFT. Yeah. And then you should be able to see whether by gauging everything you can get every CFT that value of C. It's not obvious, I think.
Well, I agree it's not obvious. I
don't think it's tautological.
Sorry?
I don't think it's tautological. I think it's a statement that is either true or false.
I agree. Well, but the thing is, like, continuous infinite symmetries haven't been, I think, like, appropriately defined yet anyways. So there might be some definition of symmetries and gauging that will, I mean, it could be by definition, right? Like, one thing that is true is that any CFT defines a kind of Lagrangian algebra in the representation category of Virasoro times Virasoro bar. And, okay, so there's already sort of hints of categorical stuff, and the question is just whether you can rephrase all of this stuff in the language of gauging. And I agree it's, like, not a priori obvious, but I sort of expect the intuition from the rational setting to hold somewhat.
So since you stressed this point that you want to define symmetries of relative theories, so you would say that also for 62,0 you would want to do something like that?
There's a big gap between 2 and 6. I'm still building up courage to go to 3.
It's because we debated this for a while, and somehow, it felt like you should construct an absolute theory. Even in 60, you find there's absolute theories, like in the paper that Pushang and Gukov and others had worked out, and then you take those, and then you write down a symmetry for them, a generalized symmetry, and a sim TFT and all that, and you can study all kinds of non-invertible things in that context. But
you're asking,
it seems like there's a conceptual question. You're stressing that one should define symmetries even for relative theories, and I just want to get a better sense of what exactly you're proposing. And
yes, yeah. So, so that's a great question. Yeah, so I do believe that there should be, I don't think you should be required to pass to an absolute theory. For example, in 2D, you can't even always pass to an absolute theory, right? So if your bulk is not Witt trivial, it doesn't have any topological boundary conditions, and I can't complete it into an absolute theory.
right, but I would say we should
Just not discuss
I would
symmetries for those
just
theories?
say we should look at two-dimensional theories, which are absolute theories, and then define symmetries for those. And it's a perspective, and I'm just trying to get a sense.
Yeah, but I think, so here we defined topological line operators supported on these boundaries, so whether you want to call those symmetries or not, I sort of personally would. I think they'll lead to selection rules in the same way. They'll behave in all the ways that symmetries we love behave. That is sort of maybe the cheaper part of defining symmetries for relative theories. It's sort of the part that mimics what already happens in absolute theories, but there's more. There's going to be pictures, like I've been drawing domes for everybody at this conference. Like there'll be pictures like this that you can draw of line operators that are attached to surfaces in the bulk, and surfaces can act in this way, and twisted sector. Yeah, there's various pictures you can draw, and I think these pictures are meaningful, and they have beautiful mathematics associated with them, and they're physically constraining. So I think why not consider them? Yeah.
I didn't follow this thing for the last 35 years or so, but there were two questions that were lingering from then, and I'm questioning whether there has been any progress on that. One was there was a concern that as we move on the C=1 line in a smooth way, the rational structure changes in an erratic way. So in what sense does it give us an approximation for the irrational theories? That's one question, and a version of it is whether it is or it's not true that whenever you have some manifold of conformal field theories, the rational points are dense in that space. So for example, in the modular space of conformal field theories or the Calabi-Yau manifold, are the rational points dense or not? So that it would give us some approximation. So these things were were very confusing, were in everybody's mind when it's some 36 years ago when I decoupled. No wonder whether there's any new insight on that.
Yeah, those are great questions. So my impression was, though I can't point to a concrete counterexample, my impression was that it's not believed that the rational points are dense in general. And as you say, Calabi-Yau sigma models I thought were supposed to be the things that furnish the counterexamples to this claim. But I don't know if there's been any work that's substantiated that. If anybody in the audience knows, please feel free to chime in. In what sense are the rational points approximations to the irrational points? That's a good question. Maybe I don't have anything terribly useful to say about that. I would say generally they're not particularly, unless they're sort of close in the Zamolodchikov metric. But besides that, I don't see any reason they need to be, yeah.
So just a follow-up comment about what Sakura said. So in 60, you can do, like in this 2D case, even if it is a relative CFT setup, you can always build it as the symmetry for absolute diagonal RCFT, right? You can just put holomorphic, anti-holomorphic as two relative boundaries of your CMTFT, and then this is the real symmetry for the absolute theory, which I think that's what Sakura would want to do. And then in 60, you can do exactly the same thing. You can
it's a little different. I want to stress that in what you did, you added a whole new non-topological sector to the theory, whereas Sakura just wanted to cap with the topological boundary condition.
I didn't say that there's a gap boundary. There isn't. You have to double it, of course.
Yes.
In 60 also?
In 2D, this is what you do, and then in 60 you can do similar things. I think it's at Sakura pointed out is first in Sergei Gukov and Pershing do paste paper, and then me and Craig and how we have a follow-up thing. So if you think you have let's say the A-type 62,0 at CFT, it is intrinsically relative. There's no way you can choose a topological boundary condition for the 70 transaminase theory, but you can always say that I have a 70 transaminase theory with two relative CFT boundaries. And then you fold it along the topological interface. This is the tensor product of two copies of that theory. That theory is absolute. It has global symmetry defined by the three-dimensional topological operators in the 7D transcendence theory.
I didn't realize that you double also in 60. Okay.
Yeah.
But that's okay. I mean, you're more than welcome to do that. And the line, so one thing I want to stress is that, maybe it's repeating a point I made earlier, whatever lines you discover in this relative setting, they will also furnish lines in the absolute setting. So if I further capped this side off with another anti-holomorphic boundary condition, I mean, this line is still a line here, and it'll still be a symmetry line of the full.
Yes, yes.
So I think maybe you can think of, if your true interest is in absolute theories, maybe you can think about this in the spirit of building blocks. You could somehow the hypothesis is that you can reconstruct all the symmetries of the full theory by understanding the symmetries of the bulk, the chiral algebra boundary conditions, and then kind of gluing them together in the right way. But I also just think it's meaningful to talk about the relative theories on their own.
Yeah, I agree. Okay, thanks.
Thanks for the question and comment.
So I have a question. First, I want to just make a comment about the last question, is that indeed, if you consider the relative one, I want to confirm what you expected. You have the relative one, you do the sandwich, you get all the absolute one. You can recover all the modular and rational CFT from that. But I have a question. Is at some point in the talk, you mentioned that you want to do the classification of all finite symmetries. By finite symmetry, do you mean that the topological defect line form a fusion 1 category? Is that what you mean?
Yeah, a finite rank fusion 1 category.
Okay.
Yeah.
So,
or another way you could say it is that the W that embeds is also rational. It has like finite index in the thing that it embeds into.
Yeah.
Sort of like the index of the embedding is related to the size of the topological lines supported on this interface.
Yeah. So then I have a comment to that, is that in the paper we wrote with Zheng Hao, we have a mathematical characterization of all such fusion category for a given 3D topological order. Given that you ask how many fusion category of topological defect can occur on the relative theory, there is a complete mathematical description of it. Simply just given by the central functor. When you have in the block you have a modular category, for any fusion category equipped with the central functor to the fusion category, then you can realize it on the boundary.
Yeah, I agree. So, but that's sort of like you're talking about, you sort of tell me all the lines that can occur on interfaces like this, right? But in order for it to be promoted to an actual symmetry of V, I have to be able to cap this picture off with a W. So if no such W exists, then I can't sort of claim that this is a symmetry of V, if that makes sense. So there's further dynamical information you have to add to this setting, in addition to the sort of categorical layer, if that makes sense.
Yeah, maybe I can talk to you afterwards. There's
Sure.
some more.
Yeah, I'd love to talk more. Yeah.
Any more questions? Okay, well, let's thank the speaker again. And we'll resume in 30 minutes.